If I have a single variable function, the stationary points are the points in the domain where the derivative is equal to 0. If f is continuously differentiable, then any local maximum or local minimum of f must be located at a stationary point. So continuously differentiable just means the derivative of f is continuous. And at one of these stationary points, f might have a local maximum, or it might have a local minimum, or maybe it's neither one. You can still have a stationary point but not have a maximum or a minimum. And the difference here is that, well, for a local maximum, you've got a place where you're increasing and then stationary and then decreasing. So your derivative is positive, and then your derivative is 0, and then your derivative is negative. If you have a local minimum, then we're talking about a place where your function is decreasing and then stationary and then increasing. So your derivative is negative, and then your derivative is 0, and then your derivative is positive again. Or it could be neither one. And neither one means maybe your derivative is positive, and then your derivative is 0, and then your derivative is positive again. And it doesn't switch from positive to negative, or negative to positive. And if the sign on the derivative is the same on either side of your stationary point, then you're not going to find a maximum or a minimum. So that's a possibility as well. So to find a local max or a local min, we look at stationary points, but just because it's a stationary point does not necessarily mean it's a local maximum or minimum. So if a second derivative is positive, this is what we call concave up. And if your second derivative is negative, this is what we call concave down. And if you're talking about a stationary point where your function is concave up, that must be a minimum. And if you're talking about a stationary point where your function is concave down, that must be a maximum. And putting all this knowledge together gives us what's called the second derivative test. The second derivative test says, okay, take the derivative of f, find the stationary points. Then take the second derivative of f, and at the stationary points, if the second derivative is negative, that's a local max. If the second derivative is positive, that's a local min. And if the second derivative is also 0, then the test is inconclusive. And we don't know what it might be. It might be a local max, it might be a local min, could be neither. Okay, so you remember that? All right, let's do one or two problems to jog our memory. Like, find and characterize the stationary points of f using the second derivative test. Well, finding the stationary points means taking the derivative, setting it equal to 0, and then solving for x. Those are my stationary points. And then here's my second derivative. That's the derivative of 3x squared, which is 6x. So where x is positive, my second derivative is going to be positive. So where x is positive, my function is concave up. And if my function is concave up, that means I have a minimum. And so I'm going to have a local minimum at the point x equals positive square root of 1/3, or positive square root 3/3, if we're being fancy. And well, if my x is negative, then my second derivative would be negative. And if my second derivative is negative, then my function is concave down. And if my function is concave down, then my stationary point must be a maximum. You okay? So without having to really graph it, I know where my maximum and minimum happen. You have already taken Calculus 1, and so you probably already get this, but if I was teaching Calculus 1, the next thing I would do is I would put it into Desmos, and I would say, look, students. I've got a minimum where x is equal to positive square root of 1/3. And I've got a maximum where x is equal to negative square root of 1/3. Okay. Next, find and characterize the stationary points of this. So quickly, we'll say the first derivative is 4x cubed, and to find stationary points, we set that first derivative equal to 0, and there's only one stationary point at x equals 0. Then we take the second derivative, and we get 12x squared, and if I plug in x equals 0 to get my stationary point, then the second derivative is equal to 0, and this is inconclusive. Right? If my second derivative is not positive and it's not negative, it's just 0, then my second derivative test is inconclusive. That means I can't tell from the second derivative whether or not this is going to be a minimum or a maximum or a neither. It could still be any one of the three. And if I go to graph this, it turns out that it is a minimum right there at that point. But I couldn't tell from the second derivative because the second derivative went to 0. So that's one example of a way it's inconclusive. Here's a different function. And again, quickly, let me find the stationary points by taking the derivative and setting it equal to 0. There's only one stationary point at x equals 0 again. Let's take the second derivative and then plug in x equals 0. And so once again, just like in the previous one, since the second derivative is 0 at my stationary point, then this is inconclusive. I can't tell whether this is going to be a minimum, a maximum, or neither. If we go to graph x cubed, this is an example of a neither. The function's increasing and then stationary point, and then it's increasing again. So this is not a minimum and it's not a maximum. So it really is inconclusive. Okay, fast forward a year, and now you're in Calculus 3. If I have a function of two variables, the stationary points are the points in the domain where the gradient of f is equal to the 0 vector. Okay? You remember gradient of f? That's the partial of f with respect to x, and the partial of f with respect to y are the two entries in my gradient vector, and at a stationary point, those are both equal to 0. This is a 0 vector, and this is what happens at a stationary point. It's the definition for stationary point. If my function is continuously differentiable in both variables, then any local maximum or local minimum of f has to be located at a stationary point. Because if one of your partial derivatives isn't 0, that means your curve or your surface. If one of your partial derivatives is not 0, that means your surface is sloped a little bit in one of those directions, and so it's not a stationary point. And again, if you were sloped it a little bit in one direction, then you could always move in that direction and get a larger or smaller value, so it can't be a maximum or minimum. At a stationary point, f might have a local maximum, it might have a local minimum. It could be neither one, right? Or there's another possibility that shows up for multivariable functions called a saddle point. So take note of the new thing. We could have a saddle point at a stationary point. I'll show you what that looks like. So the second derivative test is more complicated for multivariable functions. To do the second derivative test for a function of two variables, I have to calculate this, I don't know what you want to call it, this thing, this little lowercase d. It's the second derivative, well, I should say the second partial derivative of f with respect to x times the second partial derivative of f with respect to y minus the mixed second partial derivative squared. And here are the rules. If that number is positive and the second partial derivative of f with respect to x is negative, then f has a local maximum. If that number is positive and the second partial derivative of f with respect to x is positive, then f has a local minimum. If that number lowercase d is negative, then f has a saddle point. And if that number is equal to 0, then the test is inconclusive again. And if it's inconclusive, that means we haven't learned anything new about our function at all. We don't know if that stationary point is a local maximum, a local minimum, a saddle point, or maybe it's none of the above. There's other stuff that can happen to surfaces. And maybe it's some of those. So this is annoying, but it's something that you ought to memorize. Raise your hand if you've had linear algebra. So if you haven't had linear algebra, plug your ears. If you have had linear algebra, you can keep paying attention. This is called the Hessian matrix of a function f. And this lowercase d stands for determinant, because it's the determinant of the Hessian matrix.
Oh my goodness.
Again, don't listen to me if you haven't had linear algebra. But what we're really concerned about is like the eigenvalues. If I were to take the eigenvalues of the Hessian matrix, if one of the eigenvalues is positive and one of them is negative, it's going to be a saddle point. If both are positive, then we're talking about a minimum because it's concave up. And if both of them are negative, then it would be a maximum because it's concave down in both directions. But why do I care about the determinant? Well, the determinant is the product of the eigenvalues. You multiply your two eigenvalues together, you get your determinant. And so we're saying if the product of the eigenvalues is positive and this is negative, and if this is negative, then one of your eigenvalues is going to be negative. So the product is positive, this is negative, so one of them is negative. So the product is really a product of two negative eigenvalues because you need negative times negative to give you positive. And if both of those eigenvalues are negative, then that's concave down in both directions. So you've got a maximum. If this product is positive and one of your eigenvalues is positive, the other one has to be positive, and two positives means it's concave up, in both directions, and so it's a minimum. And then, like I said, if one of your eigenvalues is positive and one of them is negative, then the determinant will be negative, and then you get a saddle point because it's concave up in one direction, but it's concave down in the other direction. So it looks like a saddle or like a Pringles chip. I'll show you some pictures on GeoGebra here in a second. But again, those of you that haven't had linear algebra, you can now start paying attention in class again. And if you haven't had linear algebra, now you get to look forward to discussing eigenvalues in that class.
Yeah. Yeah, that was actually
Okay. Find and characterize the stationary points of f using the second derivative test. So stationary points are where my gradient is equal to 0. And the gradient is the partial with respect to x and the partial with respect to y. Set that equal to 0. And the only stationary point is the point where x equals 0 and y equals 0. Sometimes you work these problems and there's more than one stationary point, so you would want to find all of them. But in this case, there's only one value of x and one value of y. That let the gradient be equal to the 0 vector. And now for the second derivative test, I'm going to need to calculate the lowercase d thing, which is that times that minus this. And the second partial derivative with respect to x is going to be 2. Times the second partial derivative with respect to y is 2. And if I were to take a partial derivative with respect to x and y, that mixed partial, that would be 0. So this is 4. So d is greater than 0. What about fxx? That's 2. So that is also positive. And since d is positive, and the second partial derivative with respect to x or y, by the way, you could use y's instead. It's whatever you want. But since both of these are positive, that means it's concave up in both directions, and that means it's a minimum, right? We found a local minimum at my stationary point. So we type in z equals x squared plus y squared. And there we go. The point 0, 0 is a stationary point, and it's a local minimum. It's also an absolute minimum. But you can already guess what's going to happen here, but I might as well just do it and work through the thing so we get used to it. The gradient of g is the partial with respect to x and the partial with respect to y. And the stationary points are where the gradient is equal to the 0 vector. And so the only stationary point is once again the point where x is 0 and y is 0. Then for the second derivative test, I've got to take the second partial with respect to x times the second partial with respect to y minus the mixed second partial derivative squared. And that's going to be negative 2 times negative 2 minus 0 squared, which is 4. So the d is greater than 0. This is a positive lowercase d number. Then we notice that the second partial with respect to x was the number negative 2. So that second partial with respect to x was a negative number. And if the d is positive and the second partial with respect to x is negative, that means Yeah, that means this must be a local maximum. At the stationary point. So again, maybe you already could see that happening, because if I just take the negative of this surface and flip everything across the xy plane, make all the positive z values into negative z values, then of course it's going to be like that. And that is a maximum at the stationary point. All right, so let's do one that's slightly more interesting. Slowly making this interesting here. The gradient of f is, of course, the partial with respect to x and the partial with respect to y. Again, set that equal to the 0 vector. And once again, I promise not every problem ends up like this, but the only stationary point we have is where x is 0, y is 0. Now, take the second partial with respect to x and the second partial with respect to y minus the mixed second partial squared, and we get 2 times negative 2 minus 0 squared, which is negative 4. In fact, since I noticed that the d part is negative, I don't even have to really think about any one of those second partial derivatives. Because this is the thing that you got to know. This is the important part to have memorized, I guess, for your next test. All of this stuff. You don't need to know that. So yeah, don't just memorize the formula, but remember all of these bullet points too. And the saddle point deal just says if this lowercase d is negative, then it's a saddle point. I don't even care what any of the second partials are. As long as that d number is a negative number, boom, saddle point. So we are in a situation where we just found a saddle point. Now, let's look at what a saddle point looks like. As promised, it is concave up in one direction and also concave down in the other direction. So it makes a saddle. Okay, so raise your hand if you have any questions. Let me know if you have any questions so far. No? All right, what about this one? Once again, we're trying to find stationary points. So we take the gradient of g, which is the partial derivative with respect to x, and then the partial derivative with respect to y, and then we set these equal to the 0 vector. And there's only one stationary point. And again, not every problem works out like this, but these are the simple illustrative examples that I wanted to show you during lecture. And they all happen to just be so simple that their stationary points happen at the origin. Not always the case, but now we need the second partial with respect to x times the second partial with respect to y minus the mixed second partial squared. What's the second partial derivative with respect to x? 0. What's the second partial derivative with respect to y? 0. What is the mixed partial derivative with respect to x and y? 1. So 0 times 0 minus 1 squared is negative 1. So once again, my d value is negative. And again, if that's negative, our second derivative test tells us we've got a saddle point. And that should look really familiar to you. It's just rotated 45 degrees, isn't it? Okay? And I like to show those examples because it kind of illustrates maybe the intuition behind the second derivative test. Like this was a minimum because it's clearly a parabola in the x direction and a parabola in the y direction, so it's a minimum no matter which slice you're taking, the x direction or the y direction. This one was obviously a maximum because it's a downward parabola in the x direction, it's a downward parabola in the y direction. So no matter which of the two directions you look in, it was a maximum. This is a nice saddle point, and you can kind of tell from the formula that it's going to be an upward parabola in the x direction and a downward parabola in the y direction. So you get this mixture of maximum and minimum competing and making a saddle point. And those behaviors were always expressed in terms of the second partial derivative with respect to x or y. So a lot of times you get to this point and students are starting to think to themselves, yeah, but what's the deal with this whole mixed partial derivative thing? Why do we need that part? And it turns out this is a nice example because there's no behavior at all in the pure second partial derivatives. But then when you start to take a look at the mixed partial, that's the clue this time that you have a saddle point at all. Because there's really nothing happening in this function strictly in the x direction or strictly in the y direction. All of the stuff was happening at like a 45-degree angle from the x and y axes. And so how do you account for that? When your function is super boring in the x and y directions, but all the interesting stuff happens in between, that's where this term comes in. So let's do a real one. Enough with the easy examples. Let's do at least one real example in class where we've got to kind of get our hands dirty a little bit. So we're looking for stationary points. Stationary point is where the gradient is equal to 0. So I take the partial with respect to x and the partial with respect to y. And the partial with respect to x is not super easy. We're going to have to do a product rule. Remember your old derivative product rule? And the product rule says, okay, if I'm multiplying two functions, f and g, and then I take their derivative, that's going to be f prime g plus fg prime. And so this is what I'm thinking about as like the f part, and this is the g part. So f prime, well, it depends on whether I'm taking a partial with respect to x or y, because one of them's negative, one of them's positive. But we'll say the partial with respect to x would be negative 2x. And then the g prime would be e to the power 1 minus x squared minus y squared times negative 2x. Okay. And I'm sorry for being confusing, because I know this function is named f, and whenever I wrote down my product rule, I used a little f, but those aren't the same f's. Those are different f's. So now when I want to go to write down the partial of f with respect to x, I have to think about my product rule. And I'll write something like negative 2x times g plus the f part. Nope, I need a minus sign. Times the g prime part, which is negative 2x e to the 1 minus x squared minus y squared. Okay, and then the same thing, but with the partial with respect to y. And I'm still thinking about the product rule, so we got to work through this carefully. And that's going to be 2y e to the 1 minus x squared minus y squared plus 1/2 minus x squared plus y squared times negative 2y e to the power 1 minus x squared minus y squared. Okay. And I want to set this equal to the 0 vector. Now that I've found the gradient. So for one thing, let me rewrite the first entry in this vector, the partial of f with respect to x. And as I rewrite this, I'm going to factor out a few things. I'm going to factor out negative 2x. I'm going to factor out e to the power 1 minus x squared minus y squared. And then what I'm left with is 1 plus 1/2 minus x squared plus y squared. And by the way, these minus signs are not supposed to be subtracting. When I wrote those down, I was multiplying, so beware of that. And then this is supposed to be equal to 0. So, I can divide both sides by negative 2. If I divide 0 divided by negative 2, it's still 0. And also, this factor in here with the e raised to any power is always positive. You can never, ever, ever make this factor into a 0. So let's divide both sides by negative 2e to the blah, 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 and see what we get. And that means one solution is x equals 0. But that's not the only solution. The other solution is if x squared happened to be equal to y squared plus 3/2. All right, now let's take a look at the second entry in this gradient vector. See what happens if I simplify that and set it equal to 0. I will get 2y e to the 1 minus x squared minus y squared times 1 minus 1/2 plus x squared minus y squared. Set that equal to 0. Once again, divide both sides by 2, divide both sides by the e stuff, and I get y times 1/2 plus x squared minus y squared is equal to 0. And so one solution is just y equals 0. The other solution is, well, what if y squared is equal to x squared plus 1/2? Now, stationary points. Clearly, a stationary point is x equals 0, y equals 0. Now, what if x is equal to 0 and y squared is equal to 0 squared plus 1/2? That means y is equal to the positive or negative square root of 1/2. Then what if I start with y equals 0 and I set x squared equals 0 squared plus 3/2? Then we start with y equals 0 and x has to be the plus or minus square root of 3/2. And then I can probably even get more stationary points from this. Let's just combine these two equations over here and here and say then y squared must be equal to y squared plus 3/2 plus 1/2. Do you see the substitution I did? Oh, that doesn't work, does it? Because if I subtract y squared from both sides, then 0 is equal to 2. So never mind, I can't get another stationary point by trying to combine those two equations. Any of my stationary points have to start with either x equals 0 or y equals 0 and then seeing what the other does. But that's still 5 stationary points. This function has 5 stationary points. So let's take a look at what we get from doing the second derivative test here, which might be sort of non-trivial. We got to take this second partial with respect to x, the second partial with respect to y, and then the mixed partial. Right? That's going to kind of suck. Yeah, that's going to kind of suck a lot. Because either way, you're talking about a triple product rule. And maybe you know this, maybe you don't. I'll tell you how to handle triple products when you take a derivative, where you're multiplying 3 functions, f, g, and h. You're going to write f prime gh plus f g prime h plus f g h prime. And I mean, it's not even that hard. It's just that it's going to take up so much space. Like I would definitely need like a full sheet of paper to write down all of that stuff. And then that's just one of those, right? That would be just the, you know, second partial with respect to x. If, for example, if I was taking the derivative of these with respect to x, because that's the partial with respect to x. So I need to do the partial with respect to x of that stuff I just underlined in blue. And then I would have to do the same thing partial with respect to y of this green stuff, and then multiply those, and then I would also have to even do like a partial with respect to y of that stuff, which would be obnoxious as well. And so, yeah, it's going to be a lot of work. So let me tell you what I'm thinking. I'm not going to give you this question on a test, right? Because on your test, you only have 75 minutes, and I don't want you to spend all 75 minutes on one problem, right? So you're not going to get a long question on a test. The other thing, too, is I know we only have, how many more minutes? 15 more minutes. And so there's other problems I want to get to. So we're going to stop this problem here. Not that it can't be solved, but I'm not going to give this problem to you on a test. And I want to show you some other types of problems before we're done for the day. So, oh well.
So did that get pulled from like a textbook, or did you make that?
I pulled that one from an old dusty textbook off the shelf. Yeah. So I need to make a note to maybe tweak that problem for next year's Cal 3 class. All right, find the minimum distance from the point 4, 0, 6 to the plane x minus y plus z equals 3. So we've already done this semester. We've done problems where you find the minimum distance from a point to the plane, where you say, okay, my point is P, and then we're going to find some vector PQ, where as long as Q belongs to the plane, you can choose any Q you want, basically arbitrarily choose an X and a Y, and then calculate the Z, and then you find the Q point, and then you take the vector PQ, which is just Q coordinates minus P coordinates, and then you take the projection, I think, of PQ onto the normal vector, where the normal vector this time would be 1, negative 1, 1, because you look at the coefficients in your plane equation to get your normal vector. And then once you've projected the PQ vector onto the normal vector, then you can take the norm. That was like our smart geometry way of doing it back in the first part of this class. But we're going to pretend we don't know geometry now and do it a slightly dumber way.
Dumber as in easier? Is that smarter?
Or
Dumber as in this. Like, if I ask my Calculus 1 students to like find the maximum of a function, the smart kids are out there taking derivatives, setting that derivative equal to 0, finding the stationary points, doing the second derivative test, and that kind of thing. The dumb kids that are still a little bit like scrappy and a little bit motivated and want to get a good grade will just sit there and calculate the value of the function at negative 9, and at negative 8, and at negative 7, and at negative 6, and negative 5, and negative 4, and negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then they'll tell me which one was the largest value of the function and say that was the maximum, you know? That's what I mean by like the slightly dumber way, is it's like you're not necessarily going to use smart geometry skills, you're just going to be a little bit scrappy about it. Yeah?
That's what I do on test when I forget.
Yeah. Okay, find the minimum distance from the point to the plane. And so here's what I'm thinking. What's my distance formula? my distance formula is going to be the square root of x minus 4 squared plus y minus 0 squared plus z minus 6 squared. So any point x, y, z is going to have this distance away from the point 4, 0, 6. That's how we calculate distance using the Pythagorean theorem. And I want to find a minimum distance, but with one more little constraint here. And that constraint is that, well, z has to be equal to y minus x plus 3. So now I have a function that tells me the distance between any point on this plane and the point 4, 0, 6. And my function is a function of two variables, x and y. And that's fine, because we know how to find maximums and minimums of a function of two variables. You find the stationary point by setting the gradient equal to 0, and then you do the second derivative test to tell if it's a maximum or minimum. Yeah.
Did the minus 6 just go over?
Sorry, you're right. That should be plus 3 for the z and then minus 6. And so that should actually be negative 3. Thank you, Ben. Okay, now I'm going to tell you something that is a real shocker. This is a serious industry trade secret that you're not going to hear anywhere else. Minimizing this function is the same as minimizing this other function, because distance is always positive anyways. And the square root function is strictly an increasing function. It's strictly monotone. So what I'm saying is you could either try to take the gradient and set it equal to 0 and take the second derivatives of this thing and then like do the second derivative test, or you could do that procedure with this function. Maybe I should name it something else, so I don't name the same function. I don't name that different function f when it's clearly a different function. So we'll say minimizing f is the same as minimizing g, because distance is positive. I'm going to end up with a positive number. And for the positive numbers, the square root function is strictly increasing. It doesn't go up and down and up and down. It's a one-to-one function. And so if I somehow get the minimum of f, the square root, it's only because I somehow minimized the radicand. That gave me the minimum value of the square root, because it's the minimum value of the radicand. Okay? And that's way easier. It's going to be way easier to take the gradient of g and do the second derivative test on g than it was with the square root there. So, work smarter, not harder. All right, so now let's do that. I want to take gradient of g, which is going to be the partial with respect to x, which is 2 times x minus 4 plus negative 2 times y minus x minus 3. And then the partial with respect to y, which is 2y, plus 2y minus x minus 3. And set that equal to 0. And for the first entry, I'm going to go ahead and expand things out, try to collect terms. I've got like 2x minus 8 minus 2y plus 2x plus 6 equals 0. That means 4x minus 2y equals 2. For this one, 2y plus 2y is 4y minus 2x equals 3. So I could say negative 2x plus 4y is equal to 3. Let's multiply this equation times 2 and then add them together. So 8x minus 2x is 6x, and then negative 2y times 2 is negative 4y plus 4y is 0y. And then 2 times 2 is 4, 4 plus 3 is 7, and so x is equal to 7/6.
How did you get equals 3 for the second equation there?
Oh. Thank you. Glad you guys are willing to speak up about those kind of things. It saves me a lot of time if you catch my mistakes early. So what is that really? It's 4 plus 6 is 10. And x is equal to 10 over 6. Is that correct now? And then if x is equal to 5/3, take any old equation like this one, it's 12/3 y minus 10/3 is equal to 18/3. Add 10 to both sides. And then that's 12/3 y, so that's 3 over 12. 28 over 12 is 14 over 6, which is 7 over 3 for y. Okay. Man, and that was just finding the critical point. No, the stationary point. I mean, the critical point is the stationary point is a critical point. I don't know if you knew that. Every stationary point is a critical point, but not every critical point is a stationary point. It's a different term. I meant to say the word stationary point. So my stationary point is where x is equal to 5/3 and y is equal to 7/3. And we could try to do the second derivative test to find out if this is a maximum or a minimum or a saddle point or neither. But honestly, think about what the question is asking. I've got a point out in space and a plane out in space. And among all the points on the plane, is there going to be a point on the plane that has the maximum distance away from this other point? No, there's always other points on the plane that are even farther away from the point 406. There's only one point on the plane that has the minimum distance, and I only found one stationary point. So just using what we know about our problem, we can determine logically that this must be the minimum. So the minimum happens at the point where x is 5/3, y is 7/3, and z is y minus x plus 3. So y minus x is 2/3. 2/3 plus 3 is 11/3. And so that's the point on the plane closest to 406. And now, if I really want to answer the question, find the minimum distance, well, then I would have to plug in what I just found for x and what I just found for y and what I just found for z into this distance formula, right? I'd have to go back and plug in x, y, and z as 5/3, 7/3, 11/3, and put them 5/3 minus 4 squared plus 7/3 minus 0 squared plus 11/3 minus 6 squared. And that's how I could calculate my distance, for the minimum distance from the point to the plane. So there's a lot more work. But there's some lessons to be learned here, I guess. I have this request in the system with MNU inside the curriculum system that's probably going to get approved at some point this year, to create a class called Optimization Techniques. And the whole class, the entire semester, we would just be working this big survey of optimization problems that happen in real life and going over certain techniques. This is one of the big takeaways from actually using mathematics in real life in like engineering applications, for example, is that like if I want to minimize a particular function, is there a different function that I can minimize that makes it a whole lot easier, you know? And in this case, like, yeah, that makes it a whole lot easier. But that's not the only time that comes up. A lot of problems, in particular in like thermodynamics and in probability and statistics, minimization problems become a lot easier if you like take the natural log of the function, because the natural log is another function that's strictly increasing. So if I can minimize the argument of a logarithm, then I can minimize the logarithm itself. And the exponential function, e to the blah, 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 that's a strictly increasing function. So if I can minimize the argument of an exponential function, then I've also minimized the whole exponential function. So that's a really important concept for like applied math. And then the other thing too is like, if we're talking about optimization problems where you're trying to like maximize something or minimize something, you want to minimize a distance, you want to maximize a profit, whatever, sometimes you need the second derivative test to really tell you if your critical point is a maximum or a minimum. And then sometimes you don't. Sometimes you just think about it. What do you actually know about your problem? How many maximums are you expecting? How many minimums are you expecting? And you can sometimes just figure out whether a stationary point should be a maximum based on what do you know about your problem. You know, saves you some extra work. All right, y'all have a great day.